Okay, so before we get into 5.4, you guys are about to see a big chart on the board. Don't worry about writing it all down. Just get the meat of what I'm saying and write that down for your notes. What's up, guys? Today we're going to be looking at objective 5.4, which is our periodic trends objective. Now, what do I mean when I say periodic trends? Really, when we're looking at trends, we're looking at patterns throughout the periodic table. Now there are a lot of patterns throughout the periodic table, but today we're just going to be looking at what we're saying is atomic size, ionization energy, and electronegativity. Now here in a second we're going to get to those, but first of all we got to lay some ground rules on why these patterns happen. So I've gone ahead and drawn some elements up here on this whiteboard, and we're just going to look at some foundational things. Remember, when we're going down the periodic table and this column, it's called a group. When we go across a periodic table in rows, it's called a period. So lithium is in the same period as fluorine. Just remember this because that's going to be important as we go. So what I have drawn up here are just how many protons are in it, and then our electrons and their energy levels. Now what keeps electrons around an atom? Well, that's our protons. Our protons are positive charges, and our electrons are negative charges. So remember, those really attract. So our protons are constantly pulling on our electrons and keeping them close to the atom. So how much do these protons pull on electrons? Well, that's something that we call effective nuclear charge. So effective nuclear charge, again, is how much or how strong the protons can pull on electrons. And we can calculate effective nuclear charge. So let's start by looking at hydrogen. Now, hydrogen has one valence electron. And remember from last objective, which I know you guys do, that your valence electron is your outermost electron on the outermost energy level. So hydrogen has one energy level, so that's of course going to be your outermost energy level. It has one electron. So this electron is your valence electron. What does it see? What does it feel? Well, this electron feels this one proton pulling on it. So what we're going to say is that this electron feels a plus 1 CeF, or plus 1 nuclear charge. Okay, now let's move over to helium. Helium has 2 valence electrons. It also has 2 protons. So helium, we're going to look at this one. When we look at effective nuclear charge, we look at 1 electron at a time. So this electron here, it currently sees these 2 protons pulling at it. So that electron has a plus 2 CeF, plus 2 nuclear charge. Okay, it makes sense so far. Okay, now let's go back to lithium. Lithium kind of really changes the game on this. So when we look at lithium, we see that it has 1 valence electron with those 2 inner electrons on the inside energy level. So what does that valence electron feel currently? Well, while we still have 3 protons, that valence electron is being pushed out or repelled, remember, because like charges repel. It's being pushed out by those 2 inner electrons. So that electron currently feels only that 1 proton pulling at it, because it has 2 electrons pushing at it from the inside. So that kind of sets up how we calculate effective nuclear charge. So with lithium, how we calculate it is your positive charges on the inside, so your protons on the inside. So we have 3 minus your inner electrons on the inside energy levels. So it's going to be 3 minus 2. And that's still a +1 effective nuclear charge. Even though we have 3 protons, it's still only a +1 CEFF. +1 nuclear charge. Okay, let's move down to sodium really quick. So I'm going to let you guys try this on your own to calculate this. So remember, sodium has 11 protons on the inside, and now we added an energy level. So we have 2 plus 8 inner electrons. So that makes 10 inside electrons with 1 on the outside. So if I ask you guys how much effective nuclear charge this electron is experiencing, how would you go about that? So go ahead and try it really quick. Write it down. I'll give you a second. Okay, hopefully you guys kind of started writing it down, kind of know how to do it. If not, that's fine. We're going to walk through it. So, remember, we have 10 inner electrons with 11 protons on the inside. So, remember, start first with your inner protons. So that's 11 protons. Now we subtract these inside electrons. So we have 10 inside electrons equals +1. So that electron is still only feeling +1 nuclear charge. So you guys kind of see how this is shaping up? So I'm not going to move for everyone. We're going to move over to oxygen really quick. So oxygen has still the 2 inside electrons, but now we have 6 valence electrons on the outside energy level. So we calculate this the same way. So 8 protons, so we have 8 minus 2, which now gives us a +6 nuclear effective charge. So that's different than our +1 with lithium or a +1 with sodium. So what do these numbers tell us? Well, +6 tells us that oxygen pulls on its electrons more, keeps its electrons closer than lithium with a +1 nuclear effective charge. So as we're going down, you guys are going to see when you calculate it, and when we start looking at trends, I'll write up all the effective nuclear charges. But you're going to see as you go down a period or across a period, you're going to see that the numbers get bigger. And when we have bigger numbers, that means that atom pulls on its electrons more. The protons pull on the electrons more. And if you see a smaller number, that means those atoms aren't really pulling on their electrons as much as the bigger numbers. So now let's take a look with this foundational knowledge. Let's take a look at our 3 periodic trends. Okay, so before we go any further, guys, if you have any questions on this nuclear effective charge, pause the video now, find me or Mrs. Nandor, and come ask us a question. Okay, you have your chance. So here we go. Let's take a look at our first trend, atomic size. Atomic size is the distance between the nucleus and your valence electrons. So if we're looking at nitrogen, the atomic size would be the distance between the nucleus in here and the valence electrons on the outside. So how does the atomic size change as you go down the periodic table and as you go across? Well, let's look as we go down a group how atomic size changes. So let's look at this group here. Atomic size will be increasing as we go down this group. It's going to be increasing because, as you can see, we're adding energy levels every time we go down the group. Now, as you add energy levels, your atomic size is going to get bigger. 1 energy level, 2 energy levels, 3 energy levels, so on. You're going to get a bigger atomic size. So if we compare lithium and sodium, even though they're in the same group, we know that sodium is going to be bigger than lithium because it has more energy levels. That's your trend as you go down. Now let's look as you go across a period on a periodic table. So remember our good friend, effective nuclear charge, as we talked about this. So we're adding electrons, so you would think the atomic size would get bigger. but it actually decreases as you go across a periodic table. So as you go across, our effective nuclear charges are getting bigger. Now, you can remember when we talked about that, the bigger the effective nuclear charge, the more your protons are pulling on the electrons. So lithium has +1, oxygen has +6. Oxygen, protons, they're pulling more on the electrons. So as you pull more, the electrons are getting closer and closer to the nucleus, you're going to get a smaller atomic size. So if I ask you to compare oxygen and lithium, we're going to know that oxygen has a smaller atomic radius because its protons are pulling more on its electrons, making the atom smaller. Okay, so let's look at our next trend, ionization energy. Ionization energy is defined as the amount of energy needed to remove a valence electron. So let's look at how that trend goes down a group and across a period on the periodic table. Down a group. So ionization energy is basically if we wanted to take this outer electron and pluck it off and take it away. How much energy are we going to need to do that? Well, as you go down a group, remember our atomic size is getting bigger and bigger. As you get further away from the nucleus and those protons that are pulling it in, those protons are pulling that electron in less and less. Even though our effective nuclear charge is staying at +1, these protons are pulling at it less and less because those electrons are coming further away. So it's going to take a lot less energy to pluck this electron off of sodium than it is to pluck it off of hydrogen, because this electron is closer to that proton. So if we compared sodium and lithium again, the ionization energy is going to be less for sodium than lithium because it decreases as you go down a group. As you go across a period, ionization energy increases. Okay? So again, we're talking about effective nuclear charge. So if we look at lithium, again, we're looking at the energy needed to pluck it off. It's going to be a lot easier to pluck this one off because your effective nuclear charge is +1 and your proton wants that electron a lot less than an oxygen. With oxygen, it's a +6 effective nuclear charge. Those protons are pulling on those electrons so much more, it takes a lot more energy just to pull an electron off. So if we were to compare oxygen and lithium, oxygen is going to have a higher ionization energy than lithium. And that's ionization energy. Wake up! If you have to, get up, shake it out. I know this video is long, trust me, I know. But we're about to hit our last trend. So if you have to, shake it out. Let's go, let's hit this. Okay, so let's look at our last periodic trend, electronegativity. Electronegativity is kind of a cool trend. So we define it as a measure of attraction or pull that the nucleus has on electrons in a bond. So it's kind of like ionization energy, but instead of trying to pluck off electrons, we're looking at how much these protons in the nucleus want the electrons on the outside. So again, let's look at how it changes down a group and across a period. Down a group. So in this group, electronegativity is going to decrease down a group. Now it's the same kind of thing as ionization energy. These protons are a lot further away from these electrons as you get down the group because they get bigger atomic sizes. They're all related. So these protons in sodium are going to want that outer electron a lot less than these in hydrogen. So if we were to, again, let's compare sodium and lithium. So sodium is going to have a lower electronegativity than lithium because its electron is further away from the nucleus, and those protons want that electron a lot less. So remember, electronegativity decreases as you go down a group. Now, let's look at across the periodic table. Again, effective nuclear charges here. It all relates. Okay, so lithium and oxygen. With lithium, those protons, it's a +1 effective nuclear charge. So those protons, Want that electron a little bit? Well, let's look at oxygen. A +6 effective nuclear charge. These protons really want these electrons. We're really pulling on these electrons, and we're really tugging on them. And what's special about electronegativity is we look at really how it interacts with bonds. So, first of all, let's look at hydrogen and oxygen. So it's H2O with water, okay? So oxygen has a +6 effective nuclear charge, +1 for hydrogen. So in water, when two hydrogens bond with oxygen, the oxygen is going to pull on all of the electrons a lot more than what hydrogen will. And so that's what electronegativity is. It's how much the protons in the nucleus pull on all the electrons. But if I ask you to compare oxygen and lithium, oxygen is going to have a higher electronegativity than lithium. And that's the way the cookie crumbles with periodic trains.